All right, the scientific method consists of these steps, right? Observation, etc. And so the thing is, what I found as a student, I always found the stuff at the beginning of the class is so easy. By the time you get to the final, it's so easy, like the scientific method. The scientific method, because by the time the final came around, I read that scientific method, I don't know how many times, 60 times or something before the final came around. But sometimes I ask my students, what is the scientific method like right before the final, like a review, and silence. And so it blows me away sometimes that they've forgotten all the stuff near the beginning of the class, and so that's just some advice, the things that I've seen. But let's get started with chemical reactions. And so I said, how many different types of chemical reactions?
Three.
Yeah, three. And so you've learned a lot more categories of chemical reactions. Like decomposition, etc. But if we have a decomposition reaction, we can fit it into one of the three categories. And so why did I decide to arrange it in these categories rather than keeping the categories that are used in the book? And it's because of the pattern that we see. And so if I look at the three types of reactions, we have the metathesis, and then we have, I forgot what I did on the PowerPoint slides. I think I did redox next or acid base? Acid base. It doesn't matter the order, and then redox. But I chose this order because it's just a little bit simpler when you analyze what's going to happen. If you mix two chemicals together, what are the potential reactions that can occur, right? When you mix two chemicals together, or more, it doesn't have to be two chemicals. Sometimes on an exam I'll throw in three chemicals, and that screws people up. They have three different reagents there. What do you do with three different reagents, right? Or 4, or 10, or 20, it doesn't really matter. Once you know what to look for. And so why did I pick these three categories? And let me just tell you, this is based on what I call driving force for the reaction. Driving force. And so if you look at a decomposition reaction, there are multiple driving forces. Some decomposition reactions have this as the driving force. This is what's pushing the reaction forward. Other decomposition reactions have a totally different driving force. And so, so they look totally different to me. Even though, yes, okay, they're decomposition, they fit into this simple pattern, right? A, B goes to whatever. But they're totally different to me because when I look at it, what's driving those particular reactions is totally different. So metathesis all share the same driving force, right? Acid-base share the same driving force, and redox share the same driving force. The driving force is like what you guys have learned in the past, precipitation. If you get precipitation, the reaction should occur, or what else? What are the driving forces? Acid-base neutralization, going from a stronger acid and a stronger base to weaker. Weaker acids and weaker bases are more stable, right? And so typically, things that are unstable, highly reactive chemicals, going to things that are more stable, less reactive chemicals, is what drives most of the reactions that we observe, at least these ones we look in Chem 1A. And so we're looking at stability. Well, what defines stability in metathesis? Well, metathesis all fit a certain pattern, so we can look for these things that are stable in metathesis. And metathesis is precipitation, gas formation, these kinds of things, right? In acid-base, actually there are a number of types of acid-base reactions, but for the most part we're looking at neutralizing stronger acids and stronger bases to form weaker acids and weaker bases, right? Redox has a totally different, driving force than the other two, and redox reactions are looking at, the stability of like elements. For example, if somebody says your sodium intake is a little low, what should you do? Should you go and get some sodium metal to consume, or Should you go? Well, no, most people's sodium intake's too high, but just say, yeah, you know, sodium metal versus sodium ion is what they call in Chem 4, you know, Dr. Jekyll and Mr. Hyde. You know, they're totally different in stability. Or iodine, you know, you're a little low on iodine. Should you drink some iodine, I2, or should you drink some sodium iodide? What do you think? Sodium iodide, because iodine is a pretty good oxidizer and pretty reactive chemical. So you don't want to be drinking that, right? Or chlorine versus chloride. Which one's more stable, which one's less stable? Those are the things we look at in redox reactions. We look at the stability of the charge or the oxidation state on the atoms versus these two, you know, those things don't change. You know, the charge, the oxidation state in 1 and 2. And so, hence this category. But like I said, this isn't my invention. I didn't look, you know, I actually wasn't introduced to these categories until I got into a more advanced synthetic chemistry, where there are a lot more experienced synthetic chemists, you know, who divided it into more logical. You know, and when I took Chem 1A, it was like, you know, so it just felt like overwhelming number of different types of chemical reactions. How can you keep track? How can you make a prediction? Well, so let's see if my PowerPoint has a chance to check here. All right, just give me a minute here. Well, anyway, being chemists, you know, you should know about chemistry. In chemistry, we look at the physical and chemical properties of matter. And so what we're going to do is we're going to focus a lot this semester on the chemical properties of matter. You know, we want to understand, or at least have some kind of idea of how things react, both at a qualitative level and at a more quantitative level. You know? And so right now, what I want to do is just make sure, you know, qualitatively you have a good understanding, good basic understanding of chemical reactivity. Now, when you take two chemicals and try to get them to react, you know, well, how can you predict it? Do you just memorize all that stuff, right? That's one thing you could do. You could memorize it and then look for patterns in reactivity, like that. But eventually, you start thinking, yeah, I want a little bit deeper understanding of chemical reactivity. And to gain that deeper understanding, you know, chemists do this. You know, chemists, here, as well as other scientists, biologists, engineers. In fact, everybody does this because everybody's interested in properties, right? And so how can we get insight into the properties? So if I have some chemical, you know, you guys are familiar with this chemical, right? HCl. Let's do hydrochloric acid, AQ. HCl-AQ, what are the chemical properties of HCl-AQ? Yeah, strong acid, very acidic. What else? Is that it? It ionizes water. The ionization can either be considered a physical property or a chemical property. You know, by definition, would that be a physical property or chemical property, the ionization of water? In one sense, the ionization of water, it's a strong electrolyte, could be considered a physical property because it stays as HCl. HCl is a gas. You dissolve it in water, it stays as HCl, right? Although we stopped calling it. HCl gas is called what? What's the name of HCl gas? HCl gas is called hydrogen chloride gas. It's a molecular compound. It occurs as molecules. When you dissolve it in water, it ionizes. That ionization could be considered a physical property because it still stays as HCl, or it might be considered a chemical property because what happens is H+, what's the composition of H+? H+ is made up of what? What is it made out of, H+? The hydrogen ion. Maybe I need to do this. If I look at this isotope, what is it made out of? Organic chemists will call it this all the time. You know, they call it H+, they call it a proton. They call it a proton because that's what it's made out of. It's made out of one proton. A hydrogen atom is made out of one proton and one electron. You take away the electron, it's one proton. So protons used interchangeably for H+. But anyway, a proton, is it very big? No, it's extremely small. And so protons will react with water to form hydronium ion. And so this really, free protons, hydrated protons don't really exist in water. They exist as hydronium. And so that could be considered a chemical reaction. But hydronium and H+ are used interchangeably. It doesn't really matter. Well, we're getting into the properties. Well, is that it? Is that all you can say about HCl? It's a strong acid?
High electronegativity, relatively.
Well, the proton has a high.
I meant HCl. I meant HCl combined.
HCl combined doesn't really have a high electronegativity because it's neutral. Usually, the things that want electrons are going to be on the HCl. You know, if we're talking about chlorine would have a high electronegativity, but HCl is the compound. Its electronegativity would be not. I mean, this still can attract electrons. You know, the H here. And so, in a sense, the H part of the HCl is electronegative. It wants electrons. But the Cl part of HCl does not. Whereas Cl part of Cl2 really wants electrons. And so the electron density is shifted. And this is good because you're thinking in terms of, you know, maybe information that you knew before or whatever to figure out the properties. But when we're thinking about properties, you know, what are the chemical properties? There are different ways we could do this. We could do this by pattern. Okay, there are three types of reactions. What types of metathesis reactions does HCl undergo? Metathesis would be like double replacement. And so HCl would react with silver ions to precipitate silver chloride. It'd react with lead-2 ions to precipitate lead-2 chloride. It'd react with mercury-1 ions to precipitate out mercury-1 chloride. The H+ can react with lots of different anions, you know, lots. Different anions. Any kind of what we call a basic anion, it'll react with, like carbonate, form bicarbonate, etc. Those are metathesis reactions. What acid-base? Well, you could HCl will neutralize a lot of bases. A big list of them. But what redox reactions does HCl undergo? Redox reactions. Well, with sodium hydroxide, we consider that acid base. But with redox, we would consider HCl eats away aluminum metal, right? HCl will eat away a lot of metals, the active metals, we call them. And so those are redox reactions. And so we could do it systematically like this based on the patterns. But then, this kind of memorization in a bit, right? You just memorize these patterns of reactivity. But what we want to do is we want to get it into a more fundamental level or more fundamental understanding. Why is HCl good at attacking metals? Not all metals, but magnesium, it'll eat it away rapidly. I think Chem 4 we have an experiment where we use HCl to generate hydrogen gas when it reacts with magnesium, single replacement reaction. And so, if we want to understand things like, things that are outside the patterns that we memorize, then we want to look deeper into it. And when we look deeper into it, then, what do the properties depend on? The properties are going to depend on the composition. What is it made out of? Right? Composition. And so, graphite is made out of carbon, diamond is made out of carbon, right? But graphite and diamond, they're both made out of the same thing, carbon, but do they have the same properties? No, and so there's something else in addition to composition we have to look at in order to understand properties. And what is that? The structure, how are those atoms arranged? So this is what we always look at, composition and structure, and that gives us insight into properties. And so we're going to spend a lot of in Chem 1A, you spent a lot of time looking at composition and structure, and we want to apply that in Chem 1B to better understand properties. One of the things you probably want to do is go back to Chapter 3 and review oxidation numbers and oxidation states, because that's going to give us a lot of clues and insight into redox chemistry, right? Other things you should review are like Lewis structures and whatnot. What are the bonding theories? Tell me the two bonding theories, and why do we have two bonding theories? You do this for each chapter. What was the main point of that chapter? Chapter 11, whatever it was, bonding chapter. What chapter was that bonding? Bonding part 2. What was the main point of that chapter? The main point of that chapter is the two bonding theories. What were the two bonding theories, and why do we have two bonding theories? What's the difference between the two bonding theories? Uh-huh. Well, the electron repulsion is part of one bonding theory. The electron repulsion stuff comes from this bonding theory. What bonding theory is that? The electron repulsion stuff doesn't come from the other bonding theory. The other bonding theory has a different treatment of how it deals with electrons and molecules. Yeah, right. Molecular orbital theory, VS. Lewis structures is a part of the other theory. Lewis structures you generated. The theory itself is called. You see, these are like okay, what was the main point of that chapter? These are things that, people don't necessarily say, but it's something that after you go through and you read that chapter, your chapter notes a bunch of times, it's obvious, that there are. It might not be obvious. You got to make sure you fill in all the blanks, right? But the thing is, okay, what was the key point of Chapter 5? If you were to summarize the key point of Chapter 5, what would it be? You got to write these things down in your own words. A lot of people, the only thing they do is they just copy down somebody else's. And somebody else might say it, but it doesn't register, in your mind. That happened to me, obviously. That's why I always try to write down the take-home message, for each lecture and each chapter or whatever else in my own words. Summarize it, and then and you got to make sure your take-home message is accurate. So you double check that, right? But the two bonding theories are, valence bond theory and molecular orbital theory. Well, why is bonding so important? Bonding is so important because it tells us a lot about the stability, things. So we want to review that too. I said this is like the review of Chem 1A. This is kind of a review of Chem 1A because in Chem 1A we just do this qualitatively, But in Chem 1B we're going to do this more quantitatively using thermodynamics to make predictions about chemical reactions. And so since we're using chemical thermodynamics to go back and do that, tell me, what is the difference between delta H and delta U? What is delta U What is delta H and what's the difference? Yeah, delta U is the change in internal energy and okay, that's correct. Delta U is the change in internal energy. Delta U, no, delta U is the change in internal energy. Delta H is the change in enthalpy. What's the difference between internal energy and enthalpy?
One's in joules, one's work.
Work is the difference? Hmm? What exactly about it? One has work, the other doesn't have work? Or both have work and one work is in joules, the other one's in calories? What is the difference between delta U and delta H? Do you see how hard it was for me to help my friend? You know, I quickly realized it's impossible. He didn't know the answer to these. You know, sure we could go back, but it was every single point in the book he forgot. But anyway, what I need you guys to do is I need you guys to do some review. You know, you don't have much reading assigned right now because this is not, you know, I think not associated with any specific chapter, but I'd like you to go back and refresh your memory on chapter 3, you know, oxidation states. Chapter 5, you know, solubility rules, right? The bonding, what was the, you know, Lewis structures, bonding, all that other stuff, Vesper, you know, and thermodynamics. You know, for example, can you tell me the difference between enthalpy and internal energy? You know, what's your take-home? If you were to write yourself a little take-home summary, this is the difference between enthalpy and internal energy. What would you write down? W is the work done on the system or by the system. We call that W. We just call it work. But work is not enthalpy or change in enthalpy. It might be, but it's not defined. I should do that as that. So anyway, it's okay because this is the typical response from, especially after a long summer, you know. And so do some review, you know, this week and refresh. And if you have questions, ask me about that. But we're always interested in, you know, we want to know how things work, so we're interested in structure and properties. Composition, structure, and properties. So, you know, I saw this in the LA Times, so I thought this was really interesting. And so here's just the model of the Zika virus structure, composition and structure, different parts of it. And, what was it? That's from Visual Science here. And so we're interested, you know, we want to know, you know, what is it made out of, how is it structured, and how does it work, right? And that's this exact same thing we want to do with chemical reactants. We want to, you know what it's made out of, you know, how it's structured, and how it works. This is why it's important for the bonds, you know, because that's how it's structured. You know, Vesper or whatever else, MO theory, you know, how it's structured is going to tell you it's going to work. Okay, but so how should we do this then? Well, the first part, you know, there are two ways I could do this. I could start off saying, okay, these are all the, you know, I could, actually, it's going to be kind of a mix of things. We're going to do things strictly from observations. These are observations. This is a pattern. This is a pattern you should memorize. And then we're going to dabble into the theory. You know, why does it, or explain at a more fundamental level, you know, the reactivity of these things. And so this is two-pronged. A lot of factual knowledge plus some theoretical knowledge when we can. That theoretical knowledge is going to come from the theory. What's the theory? Quantum theory. Quantum theories yielded. Well, the question is, why are there two bonding theories? Somebody tell me why. Because if we have one quantum theory, how did the one quantum theory yield two bonding theories?
Electrons don't move in a predictable fashion that was accommodated by valence bond theory. So you needed to have.
Valence bond. Let me stop you for a second. Valence bond theory doesn't have electrons moving in predictable fashion. Valence bond theory, the electrons don't move in a predictable fashion. The electrons cannot be pinpointed, you know, when you define the energy. So there's some. You guys remember the Heisenberg uncertainty principle? What did the Heisenberg uncertainty principle say? Yeah, you can't predict the position and the energy with great precision. There's a limit to the precision. You can predict one or the other with pretty high precision, but that's going to sacrifice the precision in the other. Or you can predict both with not much precision. In Chem 1A, you predict the energy with high precision. That means the position of the electron is going to be uncertain, and therefore we have probabilities. Both valence bond theory and molecular orbit theory don't predict the position. There's probability associated with both those theories. So why do we have two? Well, we don't need two. We only need one. We need molecular orbital theory. Molecular orbital theory is the rigorous quantum mechanical approach to molecular, or not just molecular, but any structure. So molecular orbital theory is the full quantum mechanical approach. But how easy is it to apply quantum mechanics to solve things? Not easy. And therefore, there's a simplified approach. And so it takes some of the rigor out of the full approach, and so it's the light version. So molecular orbital theory is the full version. Valence bond theory is the quantum mechanics light, where they make some simplifying assumptions about bonding. And bonds consist of two atomic orbitals overlapping versus a linear combination. Do you guys remember LCAO, linear combination of atomic orbitals to form MOs? And so valence bond theory is the quantum mechanics light, which makes it much easier. So we spend 90% of our time talking about valence bond, even though it's less accurate. Valence bond has some serious failures. Tell me one major failure of valence bond theory. Major failure of valence bond theory. For a very simple molecule, valence bond theory gave the wrong answer. Valence bond theory was unable to predict the properties for this very simple molecule.
CO2.
No, not CO2, but close. Very close. It was a good guess. See, boy, that's a take-home message that should have been a serious take-home message, because a good part of the chapter, not a good part, but a couple of pages was dedicated to this molecule, or a page, at least a page. I got to go back and look. Close, getting closer. Not ozone, well, although ozone's part of it. Valence bond has this thing, and you're right, valence bond has what we call localized electrons, but what we do is we make the resonance hybrid to make valence bond more accurate. And so if you use the resonance hybrid for ozone, then it's okay, but there's something more serious, because we can always invoke the resonance hybrid to fix ozone plus a whole slew of others, carbonate, bicarbonate, anything with resonance structures. So that's a minor failing, but it's what we call an ad hoc, after the fact kind of fix to Like benzene's the classic example of that. You know, in benzene, all the bonds are equivalent, just C6H6. Well, I shouldn't be too hard on you guys because it's summer. You get that stuff. But it's O2. O2. How did valence bond theory fail in predicting the property of O2? Anybody remember? Wow, okay, this is a problem because they show somebody pouring liquid O2, which you can do if you cool down oxygen cool enough, it'll liquefy. So they're pouring liquid O2. Liquid O2, by the way, is very dangerous. You don't want it to come into contact with combustibles. This is a potential for explosion. But you pour liquid O2 and it's like suspended in air because, anybody remember? Oh, you know, obviously I remember because I've seen the book like 1,000 times, right? I remember it very well because the image, you know, I can clearly see the image in my head because I don't know how many hundreds of, maybe not 1,000 times, but they put it between the poles of two magnets. Do you see that? And the liquid O2 is just hovering there. You can take a look. I can bring it up. Just take a look at it. And that means that O2 is not diamagnetic as predicted by valence bond theory. O2 is paramagnetic as predicted by MO theory. And so, yeah, valence bond theory failed. It failed badly, right? And so shouldn't we abandon valence bond theory like we abandoned Bohr theory? You know, somebody asks you, heck, valence bond theory failed for this. Why are you still using it? Isn't that dumb? Really dumb. Because you don't know if you're going to get the right answer or the wrong answer. Do you? So why the heck are you using it? Valence bond theory you used to make Lewis structures and Vesper and that type of stuff. Why the heck are you still using it? You have to have an argument for this. Because, okay, this is the thing. Because this is Chem 1B, so you're progressing in science. But as you progress in science, the way you understand science is going to have to change. Because, like, even when I was an undergrad at UCLA, I only had one oral examination when I was at UCLA. But during the oral exam, you know, they can ask you any questions, right? And so the thing is, your understanding has to be, you have to, like, think, you know, what if, you know, why is this, or this kind of stuff, to be able to answer those. Because you just say, oh, there's, you know, some bonding theory or something like that, but, you know, well, not that chemistry is your major. We only have one chemistry major here, a couple of chemical engineering majors. But no matter what your major is, you want to get it to, at least when you think about these things, you want to start asking yourself these types of questions, and not to beat this point any further, but, you know, the way you start thinking about these questions is, a lot of people, they just try to stay above the surface. You know, they don't want to sink. You know, they just want to just maintain. But that's okay. But, you know, there are different levels of understanding. It's like this whole nomenclature thing I was talking about. Well, that pushes to other things. In fact, everything here. And so what you want to do, and how do you do this? Well, most people, they just kind of review for the test right before the test. And all they can do is, you know, what they recall, you know, recall whatever they memorized, right? But they don't have enough time to let it sink in, you know, into their mind so that they can build more connections. And you don't see these connections until you go over it. Like, you know, this O2 thing, I've gone over it so many times, it becomes more automatic. Everybody can do this. Well, anyway, let's continue. So we're in a chemistry class. We're trying to learn chemistry. So what is chemistry? Chemistry is the composition, structure, properties, and reactions of a substance according to American Heritage Dictionary. But you know what? I don't like this. I don't like properties. The chemist properties consist of both chemical and physical. Here they're implying that properties are just physical, and then the reactions, which are the chemical properties. Well, we combine that. And so this definition is not the same as the chemist's definition. The chemist's definition would just be the structure, composition, and properties of matter. All right, so this is semantics there, so I'm going to skip that. So this is the goal. You know, we want to understand the, what? We want to understand the properties of matter based on